Hello, everybody. Thank you for giving me the opportunity of presenting this work that has been done here in Pisa together with Davide Rossini from UNIP and Michele Campisi here in the audience somewhere. The talk is about the Ising critical quantum Otto engine. Wait. Okay. The aim of the talk is that to discuss the possibility of set up a quantum Otto engine based on the Ising chain. The question I want to answer are these three questions. In particular, I want to tell you if this engine can produce some work, if there is some role of the many-body interaction affecting the performance of such engine, and I want to discuss something about the critical enhancements since the Ising model is a critical model. To do so, I split the talk in two parts. There will be a short introduction in which I will generalize a concept that are necessary to understand the stuff of the engine. Then I will introduce the model, and then I will discuss the engine. I will present some results talking about the working engine, so this machine, the performance, and the role of criticality, and then I will conclude. I think all of you know how a classical Otto engine works. It's a four-stroke cycle. It's based on a four-stroke cycle in which you have a classical system and two thermal reservoirs. The first operation you do is an adiabatic compression. So you take the classical system, you compress it while it is decoupled from the reservoirs. Then you couple the system to the hottest reservoir between the two, and then you heat up. Then you let the system expand while being decoupled from any reservoir. So there is a mistake in the picture. And then C and D are exchanged. And then you cool down to restore the initial state. What we want to do is to make this cycle quantum. To do so, we have to introduce some concept. In particular, we have to generalize the concept of internal energy. We have to write the first law of thermodynamics and then say what work and heat are, or what we mean by work and heat. The internal energy of a quantum system is defined, we define the internal energy of a quantum system as the expectation value of the Hamiltonian. In this way, we can write the first law of thermodynamics, so we can differentiate this expectation value, and we identify the work and heat. That's really like, okay. It doesn't point, sorry. The work and the heat. The work is defined as the energy exchanged with an external source, while the heat is defined as the energy exchanged with a thermal source. With our convention, every time we have delta Q bigger than 0, the heat is absorbed, while the work delta W bigger than 0, the work is performed. Then we have to define which are the quantum version of the stroke of the engine we are considering. Okay. Thank you. So we need the working medium to choose a working medium, and we decide to use the quantum Ising chain. Then we have to define some reservoirs, and in particular, we chose a continuum of fermionic harmonic oscillator with a finite temperature. And then we had to find the analog of the adiabatic process and the isochoric process. We had some trouble. In fact, while for a classical system, the compression is well defined, for quantum system, it's not so easy to define a compression. If you consider some qubit or some, for example, a qubit that have some two energy level, you can compress the system while changing the ratio between the two energy levels. If you take a system like a quantum Ising chain that is a many-body system, the spectrum is so much complicated that you cannot easily define a compression. So we consider as a adiabatic process an Hamiltonian evolution in which, analogously to what done in the adiabatic classical process, there is no heat exchange with the external reservoirs. The isochoric process instead is a process in which no work is performed. Therefore, we just take the system and couple to the reservoirs, and we let the system change some heat with these reservoirs. Let's go. Okay, it doesn't work. Let me give more details on the cycle, because it's the most important part of this talk. So the working medium is the quantum Ising chain. For those that are not experts, the quantum Ising chain describes a set of spin that are interacting nearest neighbor interaction along the x direction, and then there is some transverse field. This transverse field is modulated in time. This system is pretty interesting because it's a free Fermion system, so we can solve it exactly. It has Gaussian eigenstates. This means that if you want to simulate them on a computer, you just have to deal with a polynomial scaling. And it is a critical system. There is a gap closure at a critical value of the transverse field that is equal to J, that from now on we set to 1. And then I had to define the BAT. So we chose a quite complicated setup. It's not so complicated. We chose a number, n number of BAT that turns out to be the same number of spin. These BAT are done on fermionic harmonic oscillator, as I told, at some finite temperature. This is the Hamiltonian describing the BAT. The two assumptions we do on this BAT are that the BATs are thermal at a thermal state at the temperature, and they have a constant density of state that we call J. The adiabatic process, as I told you, is an Hamiltonian evolution in which only work is performed. This allows us to write to evaluate the work performed during the evolution just by evaluating the expectation value of the Hamiltonian. The quench we perform is a change in the transverse field. We start from our initial value, and then we there's a linear ramp in which we quench to a final value. I want you to stress there are two questions that are important. The first one is which velocity we have to choose in performing this Hamiltonian sweep, because I told you this is a critical system. We have a gap closure, so if we want to pass across this gap, we have to reduce the velocity. If we want to have a performant machine, a performant engine, this velocity cannot be zero, must be finite. So this is an issue we have to solve. The other question is, what about, that is the same, what about quantum adiabaticity? Because when we discuss a classical engine, the adiabaticity we are talking is a thermodynamic adiabaticity in which no heat is exchanged with the external world. And this is, the classical adiabaticity is under control. The isochoric process is an incoherent evolution. There is only heat, so we can evaluate the heat exchange by just evaluating the expectation value of the Hamiltonian on the final temperature minus the expectation value of the Hamiltonian on the initial temperature. To simulate this process, we solve a master equation for the density metric of the system. Let me spend some words on this dissipator, because in general, the easiest dissipator you can simulate is a dissipator in the Limblad form. But local Limblad master equation cannot describe, in general, thermalization. For the reason, we decided to use a different formalism. We wrote some non-local Limblad operators based on our work done by Antonio D'Abruzzo here in Pisa. In particular, you can write the Limblad in the Hamiltonian eigenbasis, and this allows you to simulate perfectly the thermalization. There are some small caveats. In fact, if this is your chain, you have to couple for the simulation. To simulate the thermalization, you have to couple each spin to a BAT. All the BAT have the same temperature, the same density of states. If you write this equation here, you see that the density, the matrix, the density matrix of the system at time t follows this evolution, where this is the initial state that can be not thermal, and this is the thermal state. Essentially, this tells you that with this setup, we can simulate a system that goes toward the thermal state in an exponentially fast, with the constant that is the constant density state of the BAT. Once we have all these things, we can just generalize the quantum Otto, and we can write it this way. So this is our cycle. We started with a Ising chain. The first operation is the adiabatic increase of the transverse field. We go from an initial value of the transverse field to a final one that is larger than initial one, and we keep the system at a temperature that is the coldest between the two. Then we let the system thermalize with the hot BAT. Then we do the Hamiltonian evolution backward, and then we let it thermalize the system with again with the cold temperature. If you perform these four operations in this order, you find that your engine is actually an engine that can work. But we have some problems. There are a lot of parameters in this system. So to perform our analysis, we have to fix and vary some of them. In particular, we did the analysis by varying the system size, the initial transverse field, and the cold BAT temperature. yes, and the call back temperature, and then we fix the quench amplitude, the velocity of the quench, the hot back temperature, and the thermalization time. During the talk, I will give you some hint on what does it change if you change also this parameter. So let's see which are the first results. The first question to answer is, can this engine be useful? Solfanelli and collaborators, more or less they are in the audience, have showed that you can, there are only 4 regimes that are allowed for such a quantum engine. In particular, you can have the heat engine, so you are absorbing heat from an outer reservoir, and then you're performing some work. Then there is a refrigerator. Okay, I don't have to explain how does it work. The accelerator is something that is useless because you are performing a work on the system, and then you are just accelerating the transfer of heat from the hot to the cold reservoir. And then there is a heater in which you have a system, you perform some work on this system, and then you heat up all the baths. If we want to know if we can reproduce these 2 operational modes, and then let me show which is the diagram obtained with n equal to 50, a quench amplitude of 0.5. That means you have to consider this as the initial transverse field of the Hamiltonian evolution, then you have to add 0.5 to see which is the final transverse field. Moreover, if you are starting here, you are quenching across the critical point, that I remind you is 1. If you are quenching here, you are quenching inside the paramagnetic phase, so no gap closure, everything is fine. This has been obtained for a cold bath at temperature 0.5 in unit of the J of the Hamiltonian scale. T cold is on the y-axis. Every time you see green, the engine is working as a heat engine. Blue is a refrigerator, accelerator, heater. This is telling us that this engine actually can be useful, can be used as an heat engine or as a refrigerator. First comment on the parameter. What does it change if we consider different system size? You can see this is for n equal to 20. The shape of this diagram changed very a little, so we can, okay, it is still working in the 4 regimes I discussed before, so it's not so important to do all the simulation for different system size. If we change the temperature, for example, we consider a coldest hot bath, something changed in the shape. In particular, there is this peak around the h equal to 1.0. That is the critical point. This is the effect of the critical point that is becoming more and more pronounced because the system is colder. But still, there are all the regimes we have discussed. The last check we have to do is what does it change if we fix if we change the quench amplitude. These are the edges of this. These figures are for n equal to 50. This is how the edges move when you change the amplitude from lighter to darker, from smaller to larger quench. For the refrigerator and the heat engine. So as you can see, again, the shape changed a little bit, but still you have the 4 regimes and you can use the engine as you want. For this reason, we decided, unless specified, to fix this parameter for all the simulation. This is partially true because there will be some results in which we will study by varying n. The second question is, which is the work and which is the efficiency of this machine? Let me show the work evaluated along the cut, along this cut here. Okay, for time reason, we will focus on only on the heat engine. The whole work is focused also on the refrigerator. But let me show the heat and efficiency along these 2 cuts here. So on the left panels, we refer to the dotted line. So T cold equal to 0.1, right panel to the dashed lines, T cold equal to 0.25. Top panel is the work per unit of spin, so divided by n, and the bottom panel is the efficiency. I remind you that the efficiency is defined as the work divided by the heat extracted by the hot reservoir, and that it should be always smaller or equal than the Carnot one. The red line marks the critical point. Different colors refer to different system sizes. What emerged, and this you can notice, is that both the function for both the cut have a 2-peak structure. We have called this peak here paramagnetic because it appears at some transverse field, initial transverse fields that are in the paramagnetic phase, so they are referred to quench that are completely contained in the paramagnetic phase. The other one is defined, the critical one, because it appears a critical value as a transverse field that are smaller than the critical value. So anytime we perform the quench, we are crossing the critical value. And what is interesting is that even though, okay, you cannot see in general, you cannot see from this picture, but in general, the paramagnetic point is more performant. But you can see all the curves are overlapped. This means that there is a linear scaling with the system size. While the critical peak shows an hyperscaling with the system size. This is what we are interested in. But before this, going into details, let me tell you how does this image change when we change the other two parameters, since I promised you that I would comment on all the varying parameters, all the fixed parameters. And in particular, let me tell you how does this picture show change when we change the quench velocity. So these are the same picture for different velocity of the quench. The darker the green, the slower the quench. So the slower the quench, the closer we are to the adiabatic point. And as you can see, for very fast quench, there is a suppression of the critical peak. This is expected since we have a gap. As if we are too fast, we are dissipating energy in the excited level for both the work and efficiency. But there is a trade-off. Is that we can choose to not go too fast, too slow, and we can decide to be just a little bit under the perfect adiabaticity peak. So this is to tell you that if you want to, for example, discuss not about work but about power, okay, so thank you. You have to keep in mind that there are a lot of things, like it's not so easy to optimize which is the best velocity to work to maximize the power of this engine. Just a comment I want to do because there is no time, but I will tell you something later. About the thermalization time, I told you that the thermalization goes exponentially with the bath density of state. So you can see, you can evaluate how does the work change when you, all the simulation have been done for the same parameter of this one. This is just the work. It's a little bit different because since we are out, if the system is not perfectly thermalized, you are not still at the beginning in a stationary state. You have to perform the cycle many times to attain a stationary state, and then you can evaluate which is the mean value of this work. So I'm showing you the work per unit of spin as a number of, in function of the number of cycles for different thermalization time. And you can see that as the thermalization time is increased, you exponentially faster reach the perfectly thermalized work, that is the red line. So here again, there is if you want to evaluate which is the best point to work to let this engine operate to maximize also the power, is not so easy, straightforward to do, because you have to keep in mind that these two competing processes, and then is not so easy. So coming back to this picture that where I left you, I told you there are this critical peak with the best one, the one we are interested more. And we want to investigate the role of criticality. In particular, we are interested in what is called a critical enhancement. That is a concept introduced by Michele. That is based on the idea that at the critical point, the divergence, the fluctuation can lead to an enhancement of the performance of the engine. To search for this critical enhancement, we can look at this quantity that essentially tells you how much work is extracted with an efficiency that is always closer and closer to the Carnot one, being delta eta defined as in this way. And the critical enhancement, we talk about critical enhancement anytime we have this pi over n scaling with a n to a power of alpha, and this alpha is bigger than 0. Let's see which is the shape of pi over n for the two panels I showed before. Again, there is these two peak structure. We can see that for a big gradient of temperature, the maxima, the absolute maxima of its pi are on the paramagnetic peak. When the gradient between the two temperature of the two baths is reduced, the maxima start to move on the critical peak, meaning that maybe working in the critical regime is better than working in the paramagnetic one. We want to see how does, which is the scaling of this peak with n. So in this case, this is the scaling of the critical peak, yellow square, and then of the paramagnetic peak, brown dots. And you can see that in the paramagnetic phase, the maxima reach a plateau, so it's almost independent on the system size, while in the critical peak, At the beginning, it shows a grow with the system sign, and then it saturates, probably because we are okay. There is, okay, there is an hyperscaling with the system size. Sorry, there's no time. This is because if we want to find a connection with the concept by Michele, is because in general, the work performed by this engine is related to the magnetization of the system close to the criticality. The magnetic susceptibility of the Ising chain diverges. This is why we can see an hyperscaling. So in general, what we can conclude is that this engine exists, the critical enhancement exists, since the n-body engine, in this case, since we have an hyperscaling of the performance, behave better than a single body engines. It's better to work in this regime here, the critical one, if you have a small gradient of temperature. But in general, to work in the paramagnetic phase is better. And then also because close to the criticality, we have some quantum adiabatic troubles. And then moreover, because close to criticality, we have to deal with fluctuation. Let me conclude. This is what we learned, so that the Ising chain exists, that it's not fine to find the optical, the best working point. What we have to learn is about power, as I told you, it's not so easy if we can do different engines. In particular, I want to mention that an interesting question is to ask is what does it happen if you consider long-range interactions, and I invite you to go to Andrea Sulfanelli's poster outside here. I did it. Thank you.
Thank you very much. Quick. We have a question? Okay.
So, what is the main result? That if you are close to criticality, there is
An enhancement.
The efficiency goes closer to Carnot efficiency. That's what the result.
The main result is, in general, not just the efficiency, is that ratio, it goes, is maximized. In general, the main result, if you want, is that if you have small systems and you want to improve the scaling of the performance by just adding 1 qubit, you have to work close to criticality. So if you want that your n-body engine behaves better than n single body engines, you have to work close to criticality. This is the way to summarize it. So it's essentially.
Okay, thank you.